Okay, good afternoon. It's still afternoon, I think, everybody. I will ask my esteemed colleagues to sit down, please. Thank you very much. Nice to see so many people here. My name's Jermaine Revalier. If I haven't met you, apologies, I will meet you at some point. I am Pro Vice Chancellor Academic, and I am fortunate enough to be able to give the opening address for Professor Zhang's professorial lecture. So welcome, everybody. It's a genuine pleasure to be able to host this event today and to celebrate the achievements, the leadership, and the vision of a scholar who has, in a really short career, become an integral part of our academic community here at BNU. So Kit joined nearly 2 years ago, I think it was, as Professor in Inclusive AI. And by the way, if you can't hear me, just tell me and I'll shout a bit louder. All good. And he's a founding director of our Center for AI and Future Inclusive Technologies. He brought with him not just an outstanding research profile. There's a wind tunnel coming through that door. Just give it a push, yeah. Oh, it's even worse. Just leave it like that and take a seat. It's fine. Thank you, though. Not just an outstanding research profile and an insistence that actually AI should be for everybody and not just for those few tech executives, and that emerging technologies must reduce inequalities rather than deepen them, and that we as institutions, as universities, we should be bold in imagining a digital future that's safer, that's greener, human-centered and sustainable. So Kit has set out a vision in which technological advancement is inseparable from social responsibility. And that vision now underpins a lot of the work that he's shortly going to be talking to us about. His academic journey has taken him across a number of institutions. So before joining us, he was an associate prof at the University of Bradford, senior lecturer at De Montfort, and a senior research officer at the University of Essex, before which he earned his PhD in electrical and electronic engineering, which just scares me thinking about it, from the University of Manchester. Kit's made excellent contributions to the field of data-driven complex systems. He originated a concept called probabilistic decoupling. I am just reading, I have no idea, but I'm hoping you'll tell us what that means. As well as a number of innovations. So these are all new frameworks, new ideas that help us to reshape how we think about uncertainty, about decision-making, and intelligent system behaviors. His research spans AI, machine learning, neural engineering, and robotics, and brings coherence, rigor, and imagination to all of it. Now, Kit has a number of citations, but he's a chartered engineer, a fellow of the HEA, a fellow of the Royal Society of Arts, a fellow of the British Computer Society. He's editor on a number of journals. He has an unreal number of outputs. And in this year will be the general chair for the 2026 International Conference on Automation and Computing, which will happen right here in High Wycombe. So a short overview, but it is my great honor and my pleasure to be able to introduce Professor Kit Zhang to deliver his inaugural professorial lecture.
Thank you very much. Thank you for coming here today, and I hope you can hear me clearly. And the technician told me to use this screen because we focus on this one. Sorry about this part. And normally, I prepare this proposal. Prepare this presentation, and I go through some tutorials for some training, the skills. And they told me that I can learn some skills. The first thing is appreciate your first 3 or 4 minutes and face to the audience. Don't waste your time to thanks to this one, thanks to that one, and agree on blah, blah, blah. And I say, oh, that's not very British, you know. And so I would like to start my presentation, and thanks to Jimin for the very kind introduction. And also thanks for all the audience here for your coming. I appreciate your time. All right, and today we have around half an hour to talk about some very interesting, exciting topic. It's about AI. And it's my great honor to share my idea and my opinion for this area. The title is quite straightforward. We'll talk about the evolution of AI from dynamic model to large language model. So this is the title, and let's get it started. So first of all, I have a question, and everyone have the feeling that we talk about AI every day, and AI there, AI for that, and AI seems like can do everything for our daily job. So that is our feeling, and that's a lot of people have the same feeling that AI can do everything. But is that true? And if AI can really do everything, and what can we do? And is there any space or any gap between human and AI? So that is my first question for this presentation, for this talk. So let's leave it here and think about what can we do. I think by the end of this talk, you will have your answer. Okay, so let's get started from the industry revolution first, because we basically.
Sorry, could you speak up? I can't hear.
Okay, sure. Is it better now? Better? Is it? Yeah, it is okay. Yeah? Like this? Okay. I think that's my English problem. I'm not a native speaker. So if you can follow the slides and follow my language, that's okay. If you can't and raise your hands, I will explain again. If you still cannot understand that, leave me some time, I will teach you some Chinese. Okay. Okay, anyway, let's go back to the slides first one, and for the industry revolution. And you can see that we all get familiar about this diagram. So from industry 1, and now we achieve industry 4, and that is the current stage. And actually, if you look at all the development, it's based on the power of computing all the time. And from the first part, it's about how to use machine. And industry 2, how to use electricity. And industry 3, we use computer. And industry 4, we use networks. So that is development. And actually, what is the industry 5? That is the question. Nowadays, a lot of people say maybe AI can lead industry 5. And AI and the robotic system is industry 5. And I can see a lot of scholars, they start to doing something like industry 6, especially in Germany. They start to define what is industry 6. I think it's too early. In my opinion, we need to get clear what is industry 5 first before we go ahead. So that is the development of industry. And for the industry revolution, from the different stage, and we also have a very similar development for artificial intelligence. Actually, if you look at this diagram, artificial intelligence, we gave very early stage from the Alan Turing and this 1950s. And after that, we have some development based on the concept, and we designed the expert system. And the expert system, actually, they based on the samples. So we have two different group of people working in the AI area. And the first group of people, they define themselves and the symbolism. And because they believe that we understand the symbol first. And what is the symbol? Based on the symbol, we understand logic. Based on the logic, we generate intelligence. So that is the great group of people doing some work here. So they match the expert system. So a lot of industry design. At that area, we use expert system. So expert system, just like a micro expert, give you a lot of different rule-based, and you can use rule-based design to optimize the process. So that is the expert system. And after that, in the late 1980s and early 1990s, we have the machine learning, and in particular, it's neural network. So that is the neural network development at that time. So a lot of people working in that area, they call themselves connectionism. So they connect different artificial neural network. So that is the very important milestone. So two different group of people, they still argue with each other, and they believe themselves is right and the other people is wrong. So they have a lot of fight and debate over here. And you can see that from here, from the expert system to the machine learning, they must have some overlap from automation to the data-driven. So from automation to the machine learning, in the middle, and we have a lot of people doing the control system, and they merge cybernetics into the artificial intelligence. So this group of people call themselves is cybernetism. So, and I don't know if it's fortunate or unfortunately, I'm in this group. It's different from these two. So we merge the dynamic model into the data approach. So that is a very interesting design for this part. Actually, it's just in the middle from the stage 2 to stage 3. And based on the development from the machine learning, and since 2012, we have the deep learning. Deep learning, that means a deep neural network, and plus some reinforcement learning. So that is the part. So following this line, we go to the future. We hope we can achieve AGI, it's artificial general intelligence. Hopefully we can achieve that one by maybe, a lot of people say 2014 and 2015 maybe. And we don't know. We don't know that's that strategy correct or not, but we will see. And currently we just say over here. So that is the evolution of the artificial intelligence. So we have a lot of different tools now. So how to use them? The next question is very straightforward. How to use them? And we can use them with industry first, because we get this idea from automation, and we can see what about the traditional automation design. Can we use them together? So the topic I want to share with you is AI in industry processes. So for the industry and how to use AI, we have different idea. Actually, we got a lot of different results. And based on my research, based on different friends, different people. And the first thing is we focus on the static process. So you can see the process sometimes are different. Some process, they change in real time. They change all the time. Some of the process, they're static. They never change. All you need to do is find out the results directly. So we don't need to worry about the time. We don't worry about how they change. So if the process do not have dynamic inside, we call this is a static process. And for the static process, and the most important thing is answer yes or no. Yes or no. We need the answer yes or no. For example, you're sampling a lot of different things and trying to distinguish them from each other. And all you need to do is collect the data. Collect data based on the training, and you can diagnose and you can make decision. Something belongs to one group or belongs to another group. So all we need to do is answer yes or no. For example, you can imagine this is two different things. This is some fruit, this is apple, this is banana. And if you have a new one, and all you need to do is which group this belongs to. So that is the very urgent, very simple actually for the distinguish which group you need to put them in. And we have many different algorithms to achieve this target. And the most famous one, I think, in my opinion, is the support vector machine, SVM. This is very important. I put one tutorial link over here if you get interest, and you can visit this link and have a look. So this is very straightforward. All we need is answer yes or no. So this is one approach. And this idea can be used for many different things. the first thing I want to share with you is this is some work I worked before, and I involved in this project 5 years ago, I think. And this is for the diagnosis for some building. This is concrete. And you can see the concrete, there's some hole on it, the small hole, 3 millimeter, 5 millimeter, and 9 millimeter. So, sometimes we have a building. For example, this is a wall, and we cannot see what happens inside. For the surface, it's smooth and everything perfect. But inside, maybe have some little hole, little crack somewhere. And maybe one day, it just goes down directly without any notice. So we're trying to use some way to detect if anything happens inside. We don't want to break the surface. So this is the machine we use. We designed this one, and this is use ultrasonic. We use ultrasonic to find out what happens inside without damaged surface. So this is the design we use. And you can see we put ultrasonic over here, and with the different data we received, we can see the difference between the shape. If there's no hole, it's just a shape like that. If they have any hole for the concrete, and you can see they have a big difference from the shape. So basically, use this way, if we have a new piece of concrete, we can answer the question yes or no. Is there any crack inside? We can answer yes or no. If we say they have a problem, we can, at a very early stage, to understand what happens for the safety. Sometimes we say this is the monitoring for the health of building. And it's a very important topic now for some safety issue. So that is the first thing I want to share with you about my research. And the second one, and the picture maybe make you not very comfortable. And the second one is this one. The idea is quite similar, because if we can identify what's the problem for the concrete for some building, and also we can identify what problem for our body. So that is a quite similar idea. So we get some resources, and this is from some hospital, and all the picture is in our stomach and the column. So that is the picture come from. And what we want to do is we use image processing way, use artificial intelligence to identify the pollen over here and some from the pictures. So it's very quick, and within a very short time, we can find out what is the disease you have, what is the size for the pollen. So that is very important for our health. And you can see from the artificial intelligence, we can get results even better than some doctors, maybe junior doctors. I don't know. I'm not a medical doctor. And if use the technical way, we can quickly identify what is the problem. So it's not perfect, to be honest, because you can see if the size is 0.1, 0.2, 0.3. For the small size, we are not that confident to identify what's the difference between the size. But if the size is go to bigger, maybe 0.7, 0.8, 0.9, and we're quite confident to see they have a problem. So that is another reason we cannot replace the doctor work, clinic doctor work, but we can give the assistant, we can give the information to the doctor, and they can understand what happens. And if they made a mistake somewhere, and they will find out, go back to check the picture, to check the health image. So that is another work we use. So far, we just answer the static process, yes or no problem, to identify what the decision we have to make for using AI, using the machine learning. And the next one is something different. So what about dynamic process? It's not static anymore, because the process change all the time. Along the time, all the dynamic change. So for example, we use neural network over here, and all we need to do is trying to, based on some training, to fix what is the parameters over here. what is the parameter. But in the end, the purpose is training the network and use the network to estimate a function. So that is the principle. We're trying to estimate a function. Most of the time, it's a nonlinear function. And it's very difficult to find out this one in practice, because when we're trying to do the mathematical model, and we will see some model only work for the ideal condition. So you have to ignore a lot of facts. You have to ignore a lot of not that important component to make the model work. Otherwise, the model is too complicated. You cannot use it. So we have to design a very elegant model, but that is not accurate enough for the performance guarantee. So if we have a model already, what we can do is we use the neural network to estimate the unmodeled dynamics. And if we estimate that function, we can use that function as a capacitor to give the additional signal or additional information to the design, to the model. So in that case, we can enhance the performance for the whole system. So we divide the system into two different parts. The first part is very basic, the traditional control design and the system design. And second part is we use neural network to enhance this design, because we ignore a lot of things before. Okay, so this is the basic design used artificial intelligence. Sometimes we say machine learning, neural network, to enhance the performance for the traditional automation design, the control design. And we gave a link over here. If you get interest, you can have a look at this picture, and it's very interesting things. And we highlight this part because we have to look at this frame, and this frame just use the data to estimate the function. And based on the function, we're trying to enhance the performance. Okay, so that is the very interesting thing. One way to use the neural network. And another way, we talk about static process and the dynamic process. And is it possible to combine them together? So we still focus on a very small, tiny area. But for the big industry process, for example, this one, like that, for a big industry factory, and what we can do, we can divide it into the subsystem. And for each subsystem, we will identify the different part of the fault diagnose. So we find a lot of data, collect a lot of data. And based on each data site, we can use artificial intelligence to model in the system and go back to answer yes or no questions. So we can answer if this subsystem 1 goes right or goes wrong. And for the other system, we use the same strategy. So in the end, we use information fusion and make a decision what happens, if there's a problem or not. If there's a problem, and we can redesign the system, we can identify what is the problem, and we will find out what is the condition for the whole process. So that is the way. I want to share with you is the two-layer design, because basically we have one simple bottom design. It's a loop control. And this one has very strong dynamic and goes really fast. And they have a quick and rapid dynamic inside. And also is most dangerous part. And sometimes we say this one, if we don't change this one, we have to change some decision. For example, if they have some fault happened, we have to stop. We have to change them. So what we can do is we have another layer. It's performance layer. Sometimes we also say this is a management layer, or operational layer. And use this layer, we make decision to change the control layer. So that is the two-layer design. And for the control layer, the sampling time is very quick, maybe 0.1 second, 1 second. That is sampling time. But for this management layer, maybe it's slower, much more slower. For example, you have to make a decision using 1 hour, 2 hour, but for the loop design, it's 1 second. So they are at a different level, even for the time scale. So sometimes we say this is a multi-scale for the models. All right. That is the one example I want to share with you, and how to use AI and how to combine them together. Actually, if I have a dynamic process, but you divide it into small segments, and for each segment is static, you can consider this is static. So we go back to answer yes or no questions. So it's very straightforward. And the next one I want to share with you is this one. This is a very interesting picture. I have copyright for this picture. No worry about the license. Yeah, because I take this picture by myself. This is a very old industry factory in China. And I involved in a project before and working with a lot of engineers. The process I quickly introduce this one. And this is, where is it? This is here, the furnace. A big furnace. And for the furnace, we use electrode, 3-phase electrode, plug into the furnace. And use electric arc to heat this furnace, and with a very high temperature. The temperature is 3,000 degrees. So very high temperature. And what we can do is we use artificial intelligence neural network as a capacitor to control the current for the electrode. And also we make decision to optimize the management of the system. Because they have this process is very dangerous. You can imagine what happens here, 3,000 degrees. And if we make some wrong decision, and this one will become a bomb. And it's very dangerous to everyone. And the raw material, just like here. And the most tricky thing is this one is not fixed. The electrode is not fixed in the furnace, and it will move because the raw material comes into the furnace and it will move along with the electrode. And also the dynamic is coupled from each other because the electrode will change the position. Once they change position, and the current will change. If the current change, and the energy level will change. So it's linked to the product level directly. So you can understand this one, how to control this one is very challenging. And we use the neural network to enhance the performance here, and also enhance the performance for the optimal design, optimal siting. And this project is very successful because we save a lot of energy, and actually we save a lot of energy cost for the factory. Okay. Now the question is very straightforward. That is the traditional automation design. And we use neural network, we use artificial intelligence to support the traditional design. But the question now is, what is the challenge for the industry process if we're using AI? As we mentioned, if we want to train the neural network, we need the data. But where the data come from? And the data come from the real industry process. But the problem is nowadays, nobody really wants to share the data. Nobody really wants to share. And if you have two different industry company, you say, can you share the data with another company? Nobody say yes. They always say, no, we can't share any data. So where's the data come from? It's a key problem for our design. Another problem is, if they really share some data with you, would you like to use them? Because all the individual, all the equipment, they are different. If you have some data and you're training the data gets very good model and very good performance, it's mission impossible to transfer that performance to another one. Just because all the individual equipment, they are different. They have different dynamics. And even the same equipment. If you purchase one equipment and install in that room and install in another room, they have different dynamics. It's up to some temperature. It depends on the noise level and some other levels. So all the things, they are different. It's different from large language model. So that is the industry challenge with some real-time characteristic, because all the things happens in real time. So you know what happens for the traditional operation here is we have some engineer, some technicians, 3 or 4 in the room, and one control the raw material, one control the electrode, and another one control the emergency button. So if something happens, they will press the button and stop all the process. So that is the traditional design. But all the things happens in real time. So that means if you ask them stop and they didn't stop, and the whole process will be damaged. It's a lot of things. It's very difficult to restart. So we have to find a way to meet the hard real-time properties. So that is the industry problem, different from our computer. If your computer died, you can restart, you can reboot, and there's nothing happens, nothing different, only waste some time. But if in industry, the real time, they have some problem, you cannot easily say this is time to restart. Restart means a lot of cost. Okay, even dangerous. So the question is, now it's very straightforward. How can we work together with the large language model? Because large language model become very popular now. A lot of people say, can we use large language model to enhance that one, to improve industry, to improve that? But for industry, I think this is a question we need to answer, how to work with the large language model. Because large language model have data, industry do not have data. Basically, they go against each other. So it's very difficult to make a compromise in the middle. All right, so before we start large language model, I'm quite happy to share this one. I noticed that some people just ignore this example many times. They say the artificial intelligence from large language model. But basically, based on my understanding, artificial intelligence, the modern artificial intelligence start from AlphaGo. I think this is the landmark for AI. Before the AlphaGo, before this program, we have all the things, all we need. We have neural network, we have data, we have computer, we have everything. But nobody really created this one until the DeepMind gave the AlphaGo. So this is a long story. I want to share with you, the first thing is that the Go game is different from chess. Because the chess game is, every time you play one step, and the computer can give you the full traversal for all the possibilities. So all the things, they can go until the end. So everything, computer know everything. But for the Go game, you can never do that because you're not strong enough. Computer is not strong enough. If you connect all the computer in our world, you cannot give all the possibility for Go game. Just because for the Go game, the joint point, they have 361. So they have more than billions possibility. So you cannot use computer to go through all of them. So for Go game, it's more complicated. So the DeepMind designed this one, designed the Go game, and based on the Go game, and the first time the computer, the AI win, the AI beat human. So that is the first time this happens for AlphaGo. This is the landmark for AI. Actually, in my opinion, I share this sentence everywhere. I say this is not technology. This is not technology innovation. It's not technology innovation. Because in 1980s, we have neural network already. In 1990s, we have strong computer already. But why until 2010s, we have AlphaGo? Why? Because we change our idea. This is not a technical problem. This is idea problem. Because we first time, we believe that which one is important. The performance is more important. So in academic, we believe that for artificial intelligence, we have to explain all the things. So the computer make decision, put here or put there, and how to play the game. The computer make decision because we need to understand why they make decision like that. We use artificial intelligence, and we need to understand why artificial intelligence make decision. Use the human logic to understand computer. So that's what happens before. But since this point, and we don't worry about explainable or not, we worry about the performance. We worry about the performance. So we hope the performance better than human. That is more important. So we finally accept the black box approach. So normally we have the whiteboard, white box, we understand everything inside, and the black box, we don't understand everything inside, but we understand the input and output. So that is the first time we accept this way. Now they have following this way, we design the large language model. And now nobody knows what happens for large language model inside, how they gave the answer, because they have too many parameters inside. They have a 10 billion parameter for GPT-4, but we don't know how to do them. 10 billion is too difficult to understand that one. So is there any real intelligence for large language model? We don't know, but we don't care. We care about the results. So that is the things. So from beginning, based on the neutral language processing, and we believe that we should understand the symbol first to understand the human logic, and from language, we process the model. But basically, after that, we use computer. We don't worry about the white box. We worry about the black box. So we use computer to calculate the possibility directly. This is the self-attendance. Attention mechanism is very important in this way. And we divided one sentence into the token. And we don't need to worry about all the words. We just worry about the most important token. You can see this example. So the animal didn't cross the street because he was too tired. And we have a self-attendance over here, attention. It linked to the different token, but linked to the animal with the most high value for the weight. So we understand language from this way. Sometimes you don't understand all the words from mine, but you understand the key word, so you understand the language. So that is also the same principle for the token. Okay, and now we understand the language, and we have the deep neural network already. So what about connect them together? So if we merge them together, use deep neural network and transformer, and we gave a name for this self-attention is transformer. And if we merge them together, and we have a new structure for the model. And once we have the model, all we need to do is tuning the parameters, but we have too many parameters. And once we have the parameters, and we generate a new type of model, it's generative pre-trained transformer, and the GPT for short. So all the large language model, they use exactly the same design. And this is the large language model come from. And nowadays we have GPT and the copilots, Claude and Gemini, and etc. We have so many different large language models. Actually, they are the same. They use the same technical principle. So that is the large language model. I have to speed up a little bit. And for the large language model, you can see the challenge is very straightforward because we also lack of data. We need data everywhere. And we need to understand what is the power of computing. So even for nowadays, the computing is not enough. This word just connect the computer and the utility. It's computility to have a design for the power of computing. And energy is a very key challenge for the large language model as well. The problem is a lot of people believe that large language model is not the solution for AGI. is not the solution because they cost a lot of energy. You can compare them with the human, and what we need, just some water, just some bread, and we can think, we can write, we can do a lot of things. But for the computer, they cost a lot of electricity, they need a lot of things, additional things, for example, the coolant to control the temperature. So they comparing with the machine and the human, and we are optimized. The human is optimized, and the machine still have a big problem. So that is one interesting topic for the large language model. And also we worry about the multimodal data for the value, and also the hallucination. Hallucination is very interesting thing because Geoffrey Hinton believed that hallucination just like a dream of human. It's just like the dream. But for engineer believe that this is mistake or error. So we have a different feeling. So after that, you can see the problem. Very straightforward. Large language model cannot be used directly to the industry, unfortunately. But a large language model can support decision making. And that is the reason why we divide the industry process into different layers. The bottom layer, we cannot use artificial intelligence. At least at this level, we cannot use. But for the decision making layer, we can use artificial intelligence. So that is the design for the industry. My opinion is the automation for the dynamic model, they face to machine, but large language model face to human. So they are different. If you combine them together, it's doable, but in principle, they are different. Basically, they are different. And from this way, we can understand, because they are different, and the most tricky thing is how to design the problem. And the problem, based on my understanding, is a human-machine interaction. So automation is face to machine, and AI face to human. So we're trying to combine them together. So based on this topic, the human-machine interaction, we have some design already, and I have some special issue of the journals. And we embedded dynamic model into data-driven model. It can be used for machine, even the smart city, even our digital body. So that is the digital twins. And maybe one day, you don't need to go to hospital anymore, and you just need to share the data, share your digital twin with the hospital, and the doctor will give you the decision, give you some results directly. So that is the one way to solve the problem, human-machine interaction is digital twins. And in BNU, what we do is, this is what I did last year. We noticed the problem for digital twins, and it's not only for the single object. It can be abstract object. It can be a social community. It can be different things. So from beginning, this is the design for the industry. We have two different layers. We have the control layer. We have performance layer. And also, we can give another layer with an additional loop. This is the feedback layer from the social response. For example, I give an example quickly. So if you have some production, for example, the film, movie, and a piece of music, and you put them onto the market, and you will have some review. The customer will give you the feedback, give the comments, give a review. And all this review can be used to redesign the product, give the next generation. So you can see this is even much more slower. This one is slow, maybe 1 hour make decision, and this maybe 1 year to get full picture. So the feedback have some noise. Obviously, some people will give the bad comments, bad feedback. Some people gave the wrong feedback. And there's a lot of noise inside. So all we need to do is trying to use the human as a sensor to give all the feedback, and trying to use this feedback and use technical approach to make a prediction for the human behavior. So that is what we did last year. at BNU. So from beginning, you can see the feedback is just like a very normal normal distribution. And once we gave the feedback, use the information, and the uncertainty become very narrow. And that means we control the shape of the feedback, and we make our product better and better. So this is the results we use. That's it. That's all the things I'm trying to deliver today, and I show my reference, and this is my publication since 2025. I cannot list all of them; it's too many. And I gave a link over here if you get interested in some paper, and you can just click this link. Now we answer this question, AI can do everything, and this is question mark. Actually, no, and AI cannot do a lot of things. For example, the industry still needs automation, but we can do a lot of things. That's really important. I use this the proverb because the best time to plan the time was 20 years ago. The second best time is now. So I hope we can take some action right now to do something together. So I take action first. At this university, I create this center. We focus on a different design, and we have a very lovely name, AI Feed, and a lovely logo with the center. If you get interested, please click the button over here, and you will see the full information for the center. All right, thank you very much. That's all we're trying to deliver.